In this video, we'll be talking about dimensions of physical quantities. So first of all, what is dimension all about? Now, dimension is a system of representing physical quantities using some specific letters. All right, in this video, we're going to cover the basic and the most common ones, and that is mass, and that is mass. All right, to represent mass in dimensions, we use capital letter M. All right, so mass is represented with capital letter M. Then capital letter L, that's for length. And then capital letter T, that is for time. All right, you can also have current. Sometimes we use I, all right, or A to represent current. But in this video, we'll just cover that of mass, length, and time. Current will come in subsequent videos. So like I said, dimension is a system of representing physical quantities using some specific letters. M for mass, L for length, T for time, I or A for current. Current has to do with electricity, and I'll take dimensions related to current in subsequent videos. All right. So if you observe very well, you notice that these physical quantities are the basic or fundamental physical quantities. They are all fundamental physical quantities. So sometimes they may not ask you for the dimension of fundamental physical quantities. They can ask you for the dimension of a derived physical quantity. That's to say, a physical quantity that was formed as a result of combining fundamental physical quantities together. So example, you can be asked to calculate the dimension of volume, all right? Or maybe area. We'll take these two first. We'll start with the basic ones. Now let's start with volume. You're asked to calculate the dimension for volume. Now please take this from me. To calculate the dimension of any physical quantity, the first thing you need to do or you need to look out for is to bring out the formula for that physical quantity. All right. So whenever you're given a question on dimension, to calculate the dimension of any physical quantity, you need to bring out the formula of that physical quantity. Without it, you'll not be able to calculate the dimension. So volume, one of the most common formulas for volume we know is length times breadth times height. Now remember, in dimension, we represent length with capital letter L. So we have L, capital letter L, all right? And then breadth is a form of length. It's also difference between 2 points like length, all right? So since breadth is a form of length, both of them have the same unit, centimeter, centimeter, or maybe meter. So we represent breadth with L also, times height is also a form of length. You represent it with L. So the dimension of volume is L times L times L, which is L cube. Now let's say you want to get dimension for area. Area, one of the most common formulas we know for area, like I said, to get dimension of any physical quantity, first bring out the formula. So what's the most common formula we know? One of them is the area of maybe a rectangle, which is length times breadth. Now length, we represent it with L, times breadth, we represent it with L. So you have L times L, and that's going to give you L squared. So that's the dimension for area, and this is the dimension for volume. Now sometimes, like I said, most times we represent them using M, L, and T. In this video, I just want to cover the first three. So sometimes you may not see the dimension of area as L squared. They may write it for you in the option as M raised to power 0, L squared, T raised to power 0. Okay, so basically they can have it in this format. Now this and this, they're exactly the same. All right, remember we're just covering ML and T in this video. So this and this, they're basically the same because M raised to power 0 is 1, L squared, T raised to power 0 is 1. So this is like saying 1 times L squared, which is L squared times 1, and that's L squared. All right, so this is still the dimension for area. So let's take it up a bit. Let's see you're asked to calculate the dimension of velocity. velocity. Now, first, like I said, you need to bring out the formula for that physical quantity, or write out the formula first. That will guide you on how to go about the dimension. Now, velocity, like we know, is displacement over time. Now, displacement is a form of length, so we represent it with L. So we're going to have velocity equals L over time is T. So we have L over T. But we cannot leave it in this format. Most times in the exam, they will always want you to have your dimensions as M, L, and T. All right. In other words, M will be standing separately from L, and L will be standing separately from T. All right. Though they may have different powers, but they will be standing individually. And then also, no letter is allowed to appear more than once. So if a letter appears more than once, you simplify it. Okay. If they are not standing individually, you try to simplify it. Like in this case, we have L and T more like that together here. All right. So we simplify this by writing it this way: L times 1 over T. All right. We need to make them to be standing alone individually with their separate powers. So the dimension for velocity now is going to be equal to, now we have L times, we can simplify this now to be a numerator. To do this, we use one of our laws of indices. And what's that law all about? It says that if you have 1 over a raised to power x, okay, and you should take the inverse of this is a positive power. This power will become negative. If you take the inverse, inverse simply implies take a raised to power x to the numerator and bring 1 to the denominator. So if we take the inverse, we're going to have a raised to power x over 1. Now, according to this law, anytime we take inverse, if it's a positive power, the power will now become negative. If it's a negative power, the power is now going to become positive. All right. So this is it here. So now applying this law here, we have 1 over t. What's the power here? 1. So we have 1 over t raised to power 1. If we take the inverse, this positive power of 1 is going to become negative. So we have L times t raised to power of minus 1. If we multiply them together, L times t is LT. When we multiply letters together, we write them together. All right, so we have LT raised to power of minus 1. So that's the dimension for velocity. Now we can also calculate that of acceleration. Now acceleration, like I said, first thing you need to bring out the formula for that physical quantity. Acceleration is equal to velocity over time. All right, so what's the dimension for velocity? We've already calculated it here to be LT minus 1 over time. Dimension for time is t. Now remember, I said something here that no letter is allowed or permitted to appear more than once. If it happens, we need to simplify it. Here we have t appearing twice. Okay, we have t raised power, here we have t raised power minus 1 over t. So we need to take this together and simplify. So how do we go about that? That will give us acceleration to be equal to, we take like terms, more like we split them. So we have acceleration equals L times t raised to power minus 1 over t. So this times this is LT minus 1, like we have in the numerator, all over t. So here you have negative power and here you have positive power. So we cannot cancel them out because this is a negative power. Rather, we are going to apply one of our laws of indices, the division law. And according to the division law, we have that if you have a raised to power x divided by a raised to power y, all right, a raised to power x divided by a raised to power y, as long as the bases are the same. The bases are simply the ones carrying the power, all right? So this is our power, this is our base, this is our power, this is our base. We have a here, we have a here. As long as the bases are the same, you simply take one of the base and then subtract your powers. So we have a raised to power x minus y. Alright? So that is going to give us L times, bases are the same, so we have t raised to power, what's the power here? Minus 1. Since it's division, according to the law, we say minus. And then what's the base here? We have 1. So to simplify this, bases are the same. We take one of the base and subtract the powers. The power here is minus 1, the power here is 1. So we say minus 1, minus 1. And that will give us L times t raised to minus 1 is minus 2. So that will give us L t minus 2 as the dimension for acceleration. So let's take it up a bit and get the dimension of force. Alright, so first we need to bring out the formula for force, and mathematically force is equal to mass times acceleration. Alright, now the dimension for mass, like we already know, is capital letter M, and the dimension for acceleration is LT minus 2. We've already calculated it here. Alright, LT minus 2, LT raised to the power of minus 2. So we have mass times LT raised to the power of minus 2. So in that case, dimension for force will be m times this. That will give you m LT raised to the power of minus 2. So this is the dimension for force. Now let's take more dimensions. Let's say you want to get dimension for work done. Alright, or work. Now dimension for work, first we need to get the formula for work done. That's just the concept. First get the formula, then the dimension. So for work done mathematically is equal to force times distance. Alright, now we already know the dimension for force to be mlt minus 2 multiplied by distance. Distance is a form of length, so we represent it with L. So we have this. Now remember, no letter is permitted to appear more than once. So we have m, L times L, that will give you L squared. And then we have t raised to the power of minus 2. Okay, we take like terms basically. M, L times L, L squared, t raised to the power minus 2. So this is the dimension for work. So let's take more dimensions. Let's say we want to take that of energy. Alright. Now we know two very common types of energy. Two very common types of energy. We have the potential energy, gravitational potential energy, and we also have the kinetic energy. So let's say we want to use the formula for kinetic energy to get a dimension for energy. So kinetic energy, basically, we have half mv squared. This is the formula. So substituting their dimensions, we're going to have half times m is mass, and the dimension for mass is capital letter M. V is velocity. The dimension for velocity is, we've solved it here already, LT minus 1. So we have times LT minus 1. Now remember, velocity is squared, so say LT minus 1 all squared. Alright. Now half is not a dimension, so we ignore it. Alright. It's dimensionless, so we ignore half, and then we're going to have energy equals m times, now whenever we have a case like this, we have a power outside the bracket and then a power inside the bracket. To expand this, we need to use the power inside the bracket to multiply the power outside the bracket. We cannot multiply m and l and t together yet until we open up this bracket. Now t has a power of minus 1, l also has a power here. Power of l is 1. This l is power 1. So we have L raised to power 1, 1 times 2, that will give us 2. So we have L squared. Then we have T raised to power minus 1 times 2, that will give us minus 2. So energy will be equal to ml squared T to the power of minus 2. So this is the dimension for energy. We can also use the formula for gravitational potential energy to get the dimension for energy. So let's see it together. So again, we can use gravitational potential energy formula to get the dimension for energy, and it's going to be the same here. So doing that, we have gravitational potential energy, remember, is mass times acceleration due to gravity times height. So we have mass, the dimension for mass we already know is capital letter M. Acceleration due to gravity is a form of acceleration also. All right. So because of that, we use the same dimension for acceleration, which is LT minus 2 times height. Height is a form of length, so we use L. So that is going to give us M times L times L, that will give you L squared. And then we have times T raised to the power of minus 2. All right. So that will give us ml squared T raised to the power minus 2. So this is the dimension for energy again. So whether you're using potential energy equation or kinetic energy equation, you get the same thing. Now let's take another one, moment. Moment. So we'll get the equation for moment first, and then we'll use it to get the dimension. Now moment mathematically is equal to force times perpendicular distance. All right. So we already know the dimension for force to be ml t minus 2. Perpendicular distance is also a form of distance. It's a form of length. All right. So the dimension is L, and that's going to give us L times L. That will give us L squared T minus 2. So this is the dimension. So you can see here that moment, energy, and work done, they have the same dimensions. So some physical quantities can have the same dimensions. All right. So please have that at the back of your mind. Work done, moment, energy. The other ones, as we progress, we're going to see it. They have the same dimension. So moving on, let's take the dimension for momentum. All right. So as usual, we'll bring out the formula for momentum. Mathematically, momentum is mass times velocity. All right. So the dimension for mass we already know is m. So we have capital letter M times velocity. The dimension for velocity, remember, we already calculated it before, to be LT minus 1. Okay, so some dimensions you just can memorize them. Dimensions for like the basic ones, not basically all of them, like velocity, force, and the likes. So we have mass times velocity. So the dimension for momentum is going to be mlt minus 1. Now we can also get the dimension for impulse. So first we bring up the formula for impulse. So impulse is equal to force times time. All right, you just need to know as many equations as possible. So force, the dimension for force, we've calculated it here already. Okay, still out here on the body. ml t minus 2. Okay, multiplied by time, that's going to give us t. All right, now remember, no letter is permitted to appear more than once, so we'll simplify again. That will give us ml t raised to the power minus 2, and this is positive 1. Since they are multiplying, we apply one of our laws of indices. All right, the multiplication law that says if you have a raised to the power x times a raised to the power y. Now let's take the dimension for velocity gradient. Velocity gradient. Now basically, velocity gradient is velocity over length. Okay, if you have pressure gradient, it's also going to be pressure over length. Okay, so velocity gradient is velocity over length. So velocity, the dimension for velocity, we've calculated it previously, if you recall, is equal to LT minus 1. You can check the, you can just go back and check. So LT minus 1 over L. All right, we have L here, L here. They're both positive powers, so we can just cancel out. All right, no need stressing about any of the division laws. So the velocity gradient will be T raised power minus 1. And I hope you know this is the same thing as saying M raised power 0, L raised power 0, T minus 1. Now, we can also talk about, okay, let's see pressure gradients. Pressure gradients. Pressure gradients. Pressure gradients. Now, pressure gradients, like I said earlier, will be pressure over length. Pressure over length. Okay, so pressure, like we have here already, is ml raised power minus 1 t raised power minus 2 divided by length. Okay, we have L here and L here, so we simplify them. This is m times L raised power minus 1 over L. Then we have times t raised power minus 2. We take the L's together. Now this is a positive power and this is a negative power. So that's going to give us m times, since both bases are the same, we'll take one of the base and subtract the powers. So that will be minus 1 minus 1. Then we have times t raised to power minus 2. So that will give you m. So that will give you m times L raised to power minus 2 times t raised to power minus 2. So pressure gradient will be ml raised to power minus 2 t raised to power minus 2. As long as the bases are the same, you take one of the base and then add up your powers. So we have x plus y. All right. So we apply that law. We apply the law here. All right. We have t raised to power minus 1 times t. The bases are the same, so take one of the t's and then we add up our powers. So that will give us minus 2 plus 1. So impulse will be equal to ml t raised to power minus 2 plus 1 is a minus 1. So this is the dimension for impulse. So you can see here that impulse and momentum, they have the same dimension. All right. Now moving on, let's take the dimension for pressure. Pressure. Now pressure is equal to force over area. Okay, so the dimension for force is mlt minus 2. And area, remember we've calculated it previously to be L squared. Okay, so simplifying this, we're going to have, remember, according to our division law, we have L raised power 1 here, L raised power 2. We need to take like times because L is not permitted to appear more than once. So we're going to have M, all right, L. Now, according to our division law, if you have a case like this where the bases are the same, L here is the same as L raised power 1. In a case like this where the bases are the same, you simply take one of the base and subtract the powers. We have 1 and 2, 1 and 2 as our powers. So simply say L raised power 1 divided by L raised power 2. Taking them together, that will give us L raised power 1 minus 2. So subtract the powers. So 1 minus 2 is minus 1. And then we have t raised to power minus 2. So this is the dimension for pressure. Now next, we are going to take the dimension for coefficient of viscosity. Coefficient of viscosity. Now, coefficient of viscosity has the formula to be force over area times velocity gradient. Velocity gradient. Okay, so the dimension for force we've calculated it already to be mlt minus 2 all over area. Dimension for area is L squared. And dimension for velocity gradient, I think we still have it here to be t minus 1. So if you observe here, you see that you have L and T appearing more than 1. So we need to simplify. We take like terms. So this is going to be M times, we'll take this L and this L together. That will give us L over L squared. Then times, we have T raised to power minus 2 over T raised to power minus 1. We'll take them together, we'll group them, and then we'll simplify. So that will give us coefficient of viscosity to be m times, we can apply our laws of indices here. The bases are the same. So take one of the base and subtract the powers. This is L raised to power 1. Alright? The power here is 1, the power here is 2. The base here is L, the base here is L. So take one of the base, take any one, and then we'll say L raised to power 1 minus 2. And then we'll say times, again, we can apply it here. We'll take one of the base and subtract the powers since they are the same. They are dividing. So you have minus 2 minus, and then this is minus 1. So that will give us ml raised to power 1 minus 2. That will give us minus 1. Then we have t raised to power minus 2. Minus minus here is plus. Okay, so we have minus 2 plus 1, and that will give us minus 1. So coefficient of viscosity has its dimension to be ml raised to power minus 1, t raised to power minus 1. Moving on, we can take the dimension for coefficient of friction. Coefficient of friction. All right, so first we bring up the equation for coefficient of friction, and that is equal to the frictional force divided by the normal reaction. Now, both friction and reaction are forces. Friction is a type of force. Reaction is also a type of force. So since they are both forces, they will have dimensions to be m, l, t minus 2, and reaction to be m, l, t minus 2 as well. Since they're exactly the same, they can cancel out, and then we have it to be equal to 1. All right, and 1 is not a dimension, so we'll say dimensionless. So coefficient of friction. Coefficient of friction is dimensionless. Dimensionless. Now the next one is density. Density mathematically is equal to mass over volume. And dimension for mass is m. Dimension for volume we calculated previously to be L cubed. So density will be equal to, this is the same thing as saying m times 1 over L cube. Now applying our laws of indices, this is going to be m times, this cube here is a positive power. If we take the inverse, so L will be standing properly with its power. Take the inverse, this positive power is going to become a negative power. So that was going to give us m times L raised to power of minus 3, which is L raised to power minus 3. So m L raised to power minus 3. That's the dimension for density. M times 1 over L cube. We simplify L cubed, take it to the numerator, it becomes L raised to power minus 3, all right, all over 1. And L raised to power minus 3 over 1 is L raised to power minus 3. Now multiplying L raised to power minus 3 by M, we have M L raised to power minus 3. So that's the dimension for density. Now moving on, we can take the dimension for surface tension. Surface tension. Mathematically, surface tension is equal to force over length. All right. And force, its dimension is mlt minus 2. Length, we have it to be L, like we already know. So this is going to cancel out this. They are both positive powers. All right. So we're going to have surface tension. Dimension for surface tension will be mt minus 2. We can also take tensile stress. Tensile stress. Now, tensile stress mathematically is equal to force over area. The same with pressure, if you recall. All right. So tensile stress will have the same dimension as pressure. So let's finish it up. Force is mlt minus 2, and area is L squared. All right. So that will give us tensile stress to be now we have L raised to power 1. This is L raised to power 1, which is the same as L. So we have M L raised to power. We take like terms here. All right. L cannot appear more than once. So we subtract the powers. So we take one of the L's, since the bases are the same, we take one of them and subtract the power. So we have 1 minus 2, which is minus 1, and then T raised to power minus 2. All right. So that's the dimension for tensile stress, the same as that of pressure. So moving on, we take the dimension for tensile strain. Tensile strain. And tensile strain mathematically is equal to extension over length. That's the equation for it. Extension over length. Now extension is a form of length, so we represent it with L. Okay, it's also the difference between 2 points. It's also measured in meter or centimeter like length. So represent it with L divided by length as its dimension with to be L. So we have L divided by L, and that's equal to 1, which is a constant. All right. So we say tensile strain. All right, because 1 does not have a dimension, it's dimensionless. So tensile strain is dimensionless. And moving on, we take Young's modulus. Young's modulus of elasticity. And mathematically, Young's modulus is equal to tensile stress over tensile strain. All right, now we know tensile stress already to be ml raised to power minus 1 t raised to power minus 2 divided by strain, which is dimensionless, so divided by 1. So Young's modulus will also have its dimension to be ml raised to power minus 1 t raised to power minus 2. So Young's modulus has the same dimension as tensile stress, which also has the same dimension as pressure. All right. So next, let's take the dimension for power. You can solve dimension of power using two equations. Power is equal to work done over time. and work we know to be force times distance. You can say force times distance over time. So dimension for power, we can actually use force. All right, we've calculated the dimension to be ml t minus 2 times distance, which is a form of length l, divided by time, its dimension is t. So we're going to have power to be equal to m. Now we take like times here. We have l and t appearing more than once. We have l times l, that will give us l squared. Because they are dividing, we subtract the powers. We have t raised to power minus 2. Okay, because of division, we say minus, and then we have 1. So say minus 2 minus 1, and that will give us minus 3. So this is the dimension for power. Now power is also equal to force times velocity. We can also use this equation to get dimension for power. All right, so force, we know the dimension to be ml t minus 2 times velocity, we know the dimension to be lt minus 1. All right, so simplifying this, we're going to have m l times l, that will give us l squared. Now we have t raised to power minus 2 times t raised to power minus 1. Bases are the same and they are multiplying, so we add up the powers. So we have minus 2 plus minus 1, and that will give us ml squared t raised to power minus 2 plus minus is minus, so we have minus 3, which is the same as what we have here. All right, so that's the dimension for power. Now lastly, in this video, we'll try to find the dimension of universal gravitational constant. Universal gravitational constant. Okay, and the symbol is G, capital letter G. Now we can see this physical quantity in from Newton's law of universal gravitation, which states that the force between two masses, let's say you have two masses m1 and m2, all right, the force between the two masses is directly proportional to the product of the masses, is directly proportional to the product of the masses and inversely proportional to the square of their distances apart. And the distance between the two masses, we usually represent it with r. So we have F directly proportional to m1, m2 over r squared. Force between the two masses directly proportional to the product of the masses and inversely proportional to the square of their distance apart. So this is law of universal gravitation. But to change proportionality sign to equality sign, we must introduce our constant. So we have F equals, your constant for this law is G, universal gravitational constant. So say G m1 m2 over r squared. All right. So this is where you're going to see G. Now, how do you get a dimension for G? Now, if you recall, in all the previous dimensions we've solved, dimension for velocity, we had velocity equals, dimension for acceleration, we had acceleration equals in the formula. Dimension for force, we had force equals in the formula. Dimension for momentum, we said momentum equals mass times velocity, also like that. All right, we brought out the formula first. So we need to bring out the formula. We need to make G subject to the formula so that we can have G equals, then we can substitute our dimensions. All right, so making G subject of the formula, F here is the same as F over 1. If we cross multiply, that will give us G m1 m2 times 1. So we have gm1 m2, all right? gm1 m2 times 1 is gm1 m2 equals f multiplied by r squared. That will give us f r squared. Now making g subject of the formula, we divide both sides by m1 and m2, and that will give us g m1 m2 over m1 m2 equals f r squared over m1 m2. Remember, our goal here is to make g subject of the formula, all right? So that it would be like all the previous ones we've been solving, where the physical quantity, that the dimension of the physical quantity we are looking for, or the physical quantity where the physical quantity whose dimension we're looking for was always subject of the formula. So we have g equals f r squared over m1 m2. At this point, we can substitute the dimensions. So dimension for force, we have it to be ml t minus 2. R is distance. The dimension for distance, we have it to be L squared. All over mass have dimension to be M. Alright, capital letter M. So we have M times M. And that will give us dimension for G to be, here we take like terms. So we have M times M over M. Let's take all the M's together. We have M all over M times M. That will give us M all over M times M. Then times, we have L and L here. So take them together. We have L times L squared. And then we have T raised to the power minus 2. Alright, so that will give us G to be equal to this M times M over M all over this M all over M times M. So this is going to cancel out one of this, and they will be left with 1 over M times, this is a positive power and they're multiplying, so we can add up the powers, and that will give us L raised to power 1 plus 2, that is 3. That will say times T raised to power minus 2. So 1 over M, M here has a positive power, so if we take the inverse, it's going to become negative. So we're going to have G equals M all raised to the power of minus 1. Alright, and then we have L cubed T raised to the power of minus 2. So this is the dimension for G, which is universal gravitational constant.